Good morning, everyone. This is the third lecture in online short course on satellite meteorology applications in weather and climate studies. This lecture is also being conducted under the banner of Azadi Ka Amrit Mahotsav. The title of today's lecture is Applications of Satellite Data in Indian Summer Monsoon Studies. To start with, let us see what is monsoon. How do we define this? So monsoon is a system where a reversal in the winds and precipitation patterns are observed. This is also a climatological feature that covers almost half of the tropics, that is approximately 1/4 of the global surface, and a region where 65% of the world's population lives. And this system provides sufficient water to host one of the most successful agricultural system. As all of us know that Indian region is getting most of its economy through the agriculture, and we have the rain-fed agriculture, and 80% of the rainfall is received over Indian region through the Indian summer monsoon system. Now, there is a classical criteria proposed by Ramage in 1971. As per this criteria, monsoon is specified as follows. The prevailing wind direction should shift by at least 120 degrees between January and July. The wind direction persists for at least 40% of the time in January and July. And average wind speed should exceed beyond 3 meters per second, and pressure pattern should satisfy a steadiness criteria. So based on this criteria proposed by Ramage, the yellow patch shown here in this picture is the monsoon domain, and our Indian subcontinent is also a part of this monsoon domain, which satisfy all these four criteria proposed by Ramage. Now what happens during the summer time? The land region is having a low heat capacity. Therefore, giving the same amount of the energy to the land and the ocean, land become warmer very quickly. So and thereby there is a creation of low pressure system over the land region. And with the onset of the summer season, highest surface temperature during the year are also observed in the month of May. So we see several incidents of heat waves due to the creation of this low pressure system and high temperature over the land region. And the surrounding oceanic region, having the high heat capacity, it takes longer to become warmer. Therefore, the ocean towards the south and surrounding Indian land region remains less warmer. Thereby, there is a creation of high pressure system over the oceanic region. And therefore, a strong thermal gradient is set up. Because of this low surface temperature over the land and high sea surface temperature over the oceanic region. And this temperature gradient, due to the differences in the temperature, result in the reversal of the winds. Generally, winds in this region, the tropical region, winds are easterlies. They move from east to west. But due to this land-ocean thermal contrast, we have the high pressure system here and low pressure system here on the land region. Therefore, the easterlies, which are coming from the east, moving towards the west, it changes their direction and moves towards the Indian land region. So winds basically becomes westerlies or southwesterlies. There is another important feature that is known as Intertropical Convergence Zone, ITCZ. So Indian summer monsoon is also characterized by the northward excursion of ITCZ. And as the winds from the oceanic region start moving towards the land region, pick up moisture from Arabian Sea and Bay of Bengal. And this moisture is basically trapped by the Himalayan ranges and the Hindu Kush in the Indian subcontinent itself. And this moisture is released over Indian land region in the form of rainfall. So this is the picture illustrating the surface pressure across the globe in the month of July. So monsoon set up start in this Indian subcontinent region, or the onset of the monsoon is declared in the first week of June. 1st June is the climatological date. So we see the monsoon for the 4 months time period, starting from June till September. And this is the month of July. As per the Ramage criteria, the steadiness pattern should satisfy for this monsoon domain. Therefore, in the month of July, we also observe, still we observe this high pressure system over the oceanic region, low pressure system over the land region. And this pressure differences and the thermal gradient actually introduce this reversal in the wind direction. And then you can still see this cross equatorial flow because it is crossing the equator here. First of all, and the winds are becoming westerlies or the southwesterlies, carrying moisture over the Indian land region. July is also the month which is known as the principal rainy season. July and August are the 2 months in which Indian summer monsoon pour maximum rainfall over Indian land region. So the data as shown here is basically the reanalysis data from NCEP and CAR. And this is the climatology of surface pressure starting from 1959 to 1997. There is another important feature of Indian summer monsoon. The data is basically GPCP, the Global Precipitation Climatology Project, which uses several inputs from satellite, like it takes precipitation estimates from spatial sensor microwave imager, emission and scattering based algorithm. This is basically a microwave imager which uses two different algorithms, scattering based for the land region, emission based for the oceanic region. So the rainfall or the precipitation retrieved from this particular satellite using these two algorithms have gone into the this particular GPCP dataset as an input. It also uses GOES precipitation index as an input. It uses outgoing long wave radiation index (OPI), rain gauges dataset wherever the ground-based network is available. The datasets are also used as an input for the GPCP. And TOVS sounders on NOAA polar orbiting satellite are also act as the input for this particular product. So using this GPCP data for a long-term time period, approximately 25 years, this is the July precipitation. So the mean of this particular month over these many years, you can see there is a band of high rainfall. If you compare the colors with this color bar, you can see this shades of blue and the pinks are ranging from 28 to 40 centimeter, means 260 to 400 millimeter. So this high rainfall band is actually observed across the globe. So it is having a global structure. It encircles the entire globe, having the maximum rainfall within this band. This is known as ITCZ, Intertropical Convergence Zone. Intertropical Convergence Zone is the zone where the maximum rainfall of the globe is observed. This is also the zone where we observe the maximum cloud cover. And during the monsoon season, see, July is the principal rainy season, July and August. So during July, this is the climatology of the July. You can see over Indian subcontinent, there is a band of high rainfall. At the same time, we can see a band of high rainfall towards the south of Indian land region. So Indian summer monsoon is also characterized as the dual band structure of ITCZ. This is also one of the important feature of Indian summer monsoon. Now, during the monsoon season, we observe several changes, and these seasonal changes are characterized by a variety of physical mechanisms which produce strong seasonal winds, which carry moisture over the Indian land region, and we also witness a wet summer and a dry winter. These changes that we observe over Indian land region during the monsoon season are governed by the physical ingredients which are listed here. First of all, we require the land-sea temperature contrast, which help for the reversal of the wind direction and make the easterlies, the westerlies or the southwesterlies. Planetary rotation is also a very important component because Earth rotates its axis, and this rotation actually introduces swill in the wind direction. Therefore, we observe the southwesterlies during the monsoon season. The important ingredient for the rainfall is the moisture. And Indian land region is surrounded by the seas, Bay of Bengal and the Arabian Sea. Therefore, we have a source of moisture around the Indian subcontinent. Then orography is also one of the important parameter or the important physical ingredients because it provides the mechanical uplifting to the clouds and it is responsible for the warm rain processes in this region. Orographically dominated region over India, like Western Ghats and Northeast Indian region, receive the maximum amount of the daily rainfall during the monsoon season. So the monsoon rainfall is observed during the 4-month season, and there is a term which is known as the onset or the arrival of the monsoon, and further its advancement across the Indian subcontinent is defined based on 3 different parameters defined by Indian Meteorological Department. So how the Indian Meteorological Department defined the onset of the monsoon over Indian region? They uses different stations, 14 stations like Minikoi, Emini, Thiruvananthapuram, Punalur, Kollam, Alappuzha, Kottayam, Kochi, Thrissur, Kozhikode, Thalassery, Kannur, Kodulu, and Mangalore. So each rainfall after 10th of May, which is of the order of 2.5 millimeter or more for 2 consecutively days, the onset over Kerala is declared on the second day, provided the following criteria are also met. So the other criteria are the winds and the OLR. So depth of the westerlies, because we have seen that there is a reversal in the wind direction. So the westerly winds should be maintained up to 600 hectopascal. That is the height approximately 4 kilometer. Up to a height of 4 kilometer from the surface, we should witness the westerlies in the box from equator to latitude 10 degree north and longitude 55 degree north to 80 east to 80 degree east. So the zonal wind speed over the area bounded by latitude 5 to 10 degree north and longitude 70 to 80 degree east should be of the order of 15 to 20 knots at 925 hectopascal. So we should observe the very strong winds, and the depth of the westerlies should be maintained up to 600 hectopascal. Apart from this, the outgoing long wave radiation, which is nothing but a proxy of rainfall, should be below 200 watt per meter square in the box confined by latitude 5 to 10 degree north and longitude 70 to 75 degree east. Apart from onset and the advancement of the withdrawal of the monsoon or the end of the monsoon season should start from the extreme northwest part of India. So over this region, after the 1st September, if we notice the end of the rainfall activities for consecutively 5 days, it should happen continuously for 5 days, then we can declare the withdrawal of the monsoon from this region. Apart from that, we should also note the following: the establishment of anticyclone in the lower troposphere, that is up to 850 hectopascal and below, and considerable reduction in the moisture content that we infer from the satellite water vapor imageries and T5 diagram. So given these two definitions, IMD has generated these two climatological chart for the monsoon onset, its progression and withdrawal. So as you can see that monsoon start from the Kerala on 1st June, and then there is a gradual progression across the Indian subcontinent. 1st June is the date for the monsoon onset over Kerala climatologically. However, there is a standard deviation of 8 days. So 1st June plus minus 8 days, we can anticipate the arrival of the monsoon over Indian subcontinent. Then it gradually progressed across the Indian subcontinent. And this is the region, the extreme west part of India. It received rainfall around 8th of July. So this is the region which received the monsoon rainfall towards the end of the start season. It also witnessed the withdrawal at the earliest. So this is the region, this one, the 20 September and 17 September are the dates of the withdrawal from this part of the Indian region. And gradually we can see that monsoon season end over the India by 15th of October. So these two are the climatological map of these two dates. The base data for this onset date is from 1961 to 2019, whereas for the withdrawal, IMD has used data from the 1971 to 2019. See, we don't see that downpour in a continuous manner throughout the monsoon season. There is a gradual. Don't anticipate same amount of the rainfall over Indian region. So this data is from the rain gauges and has been plotted from the period 1871 till 2016. Here the rainfall anomalies are plotted on this graph. So anomaly is nothing but the departure from the long-term mean. So here the base period is taken as 1871 to 1990. And based on this period, if we see the mean monsoon rainfall, that is approximately 852.3 millimeter. So during the 4-month season, Indian region witnessed this much amount of the rainfall. Standard deviation of the rainfall during this season climatologically is about 84.3 millimeter. So if we just compare the mean and the standard deviation, the coefficient of variation of rainfall over this region is about 10%. So if there is a fluctuation within 10% of this value, or the anomalies which are fluctuating within +10 to -10, those years of the Indian summer monsoon are considered as normal monsoon year. However, there are still variations, but they are fluctuating within +10 to -10, and the anomalies which are exceeding +10 are the years during which Indian region witnessed excess summer monsoon rainfall. So these years are 20 over this much of the time period. So 20 excess years have been witnessed over Indian region. Likewise, these are the negative anomalies. These are the deficit years. So altogether 20 excess year and 27 deficit year have been noted over Indian region starting from 1871 to 2016. And here the lines are shown as mean +1 standard deviation, mean -1 standard deviation. So as I mentioned, the anomalies which are crossing this +10 or the -10 are the extreme years on the interannual scale. Now the applications of the satellite data set for the study of Indian summer monsoon. So why we should use satellite data sets for the monitoring of the monsoon progression? Because significantly expanded coverage we get through the satellite data sets. We get a continuous coverage, that too also at a very good spatial resolution. If we use only the ground-based measurement like rain gauges or the AWS, in yesterday lecture you people have seen that the network, the ground-based network is patchy and it is not homogeneously distributed. Therefore, at some of the location we miss the observations. Likewise, we are monitoring the rainfall or other parameter from space. So there is no problem of the beam blocking. There is less need for calibration of satellite data set. Often it is done using only one instrument on board the satellite, and this supplement the ground-based estimates. So wherever we don't have the ground-based measurements available, we rely upon the satellite data sets. Satellite data sets are also crucial to assimilate in the numerical weather prediction models and also in the global model for the improved forecast of the weather patterns. So here the rainfall progression is shown based on the global precipitation mission dataset. GPM is a satellite which was launched in 2014, and in this animation the rainfall for 8 days has been shown. As you can note here, the data set is available for every half an hour. So such a diurnal variability of the monsoon season rainfall we can see in this animation. So as I already mentioned that there is a physical ingredient, that is orography. So this part of the Indian region, the Western Ghats, is dominated by the orography. And here a very good amount of the rainfall, a very high amount of the rainfall is noted during this 8 days time period. So we also have seen the diurnal variability and also the accumulation of the rainfall in this region. It's a high amount of the rainfall accumulated over here, as well as in the northern part of India and the northeast Indian region. So the rainfall accumulation here and also in the hilly region is actually responsible for initiating disasters like debris flow, landslides, and floods. So given such a high spatial temporal resolution data set, we can monitor the diurnal signature of the rainfall. We get the information at every half an hour, and we get information continuously for every 10 kilometer, because the resolution of this data set is 0.1 degree by 0.1 degree. So approximately at every 10 kilometer by 10 kilometer square grids, we have the data sets available over this region. And this data is actually available globally. Satellite-based estimates. Apart from GPM, there are several products available from the satellites that can be used for various kind of the studies. Here, different satellite sensors are shown and how the data sets are collected from these sensors are shown. This is the GPM constellation, so Global Precipitation Mission constellation status. So various satellites are actually giving input to this GPM data set, and through that it has developed the IMERGE product, which is available at a very high spatial and temporal resolution. So here is a list of the data sets like Global Precipitation Climatology Project, GPCP, and it is available from 1979 till date, and it uses various data sources from satellites. Because for the climatological analysis, you just need to get the coarser information. Suppose you want to do the analysis for the Danville variability, you may use the TRMM3B42 dataset, which is available at 0.25 degree by 0.25 degree resolution. The dataset is available at 3-hourly scale as well as daily scale. But the TRM is a tropical rainfall measuring mission. It provides data set between 50 degrees south to 50 degree north. So it was dedicatedly designed for the tropical region. The data set is available 1998 till 2018, and it uses various data sources like TRM microwave imager, combined instrument, SSMI, SSMIS, etc. Likewise, there are several other products listed here. So depending upon the user need, the different products can be chosen, because you can see the time period of their availability is also different. So accordingly, the user can define what kind of analysis want to do using the satellite data set. So apart from these listed products, we also have datasets available from Indian National Satellite System 3D and 3DR. So these two satellites are the geostationary satellite. They derive rainfall products over Indian sector, and the datasets like from the IMSR algorithm, the product is IMR. There is a hydro estimator rainfall, that is the product name HE-RAIN, are available up to 5-kilometer resolution at every half an hour from 2013 onwards. But if we use these two datasets, 3D and 3DR, 3DR was launched in 2016. 3D products are available from 2013. But if you use the two products in tandem, you would get information at every 15 minutes at about 5-kilometer resolution. So finite scale analysis, particularly the extreme rainfall events analysis, the cloudburst analysis, can be done using the geostationary INSAT 3D and 3DR satellite data sets. Now here is the potential of the INSAT data for the monitoring of the monsoon progression across Indian subcontinent. So these are the pictures shown for the 2022 monsoon season. Here you can see the strong cross equatorial flow, and also the Somali jet was nicely captured by the winds derived from the INSAT data set. Here a very clear southwester flow can be seen. This is associated with the positive relative vorticity, accompanied with the lower OLR values. As per the definition given by IMD, OLR value should be below 200 watt per meter square within this box. So the same we witness here for 28th of May. Likewise, on 29th of May, the values remains lower, below than the 200 watt per meter square. And in association with these dropped OLR values, we also see high amount of the rainfall in this region. And therefore, the cross equatorial flow, Somali jet, positive vorticity, reduced OLR, and enhanced precipitation. These are the characteristics of the monsoon, were nicely captured by the INSAT-based data set. The 850 hectopascal winds, outgoing long wave radiation, and GPI precipitation data set. So in 2022, the monsoon rainfall arrival over Indian subcontinent was declared on 29th of May 2022. Based on all these criteria, because the westerlies were found up to a depth of 600 hectopascal, the OLR values were very low, and this animation is showing the progression of the monsoon rainfall across Indian subcontinent starting from 28th of June till 15th of June. And during this time period, you would see that the monsoon rainfall has covered almost entire Indian subcontinent in association with the lower OLR values, because lower OLR values are nothing but the proxy for the rainfall. So wherever the low OLR values are noted, those are the regions of high clouds or the more cloud cover, because cloud actually reduce the OLR or the outgoing long wave radiation data to be recorded by the satellite sensor. So whenever clouds are present, long wave radiation is recorded by the satellite sensor, which is lower than the values whenever no clouds are present. So based on the data sets, we can infer whether the clouds are present over land or not, or clouds are present over oceanic region or not. So that kind of analysis can be done using the satellite based outgoing long wave radiation, and we can get first hand information about the rain bearing system using only the OLR data set. So as defined by the IMD, there are the stations, some 16 stations are there. Out of those, the 4 stations are shown here. And here you can see that the high amount of the rainfall, which is more than 2.5 millimeter per day, was noted for consecutively 2 days. Therefore, the high amount of the rainfall arrival over based on that, IMD declared the monsoon arrival over Indian region on 29th of May. Here you can see that good amount of the rainfall was received over these stations in the last week of May. So INSET data has shown the potential of the monsoon progression monitoring. Likewise, this is a progression of southwest monsoon season for 2023. So during this year, Indian region witnessed monsoon onset on June 8, which was also accompanied with the development of the tropical cyclone Biparjoy in Arabian Sea. So as we can see in this animation, the high amount of rainfall is noted along the path of the tropical cyclone. This is the path of the tropical cyclone Biparjoy. So after the Biparjoy made landfall over Indian land region in the state of Gujarat, its remnant was responsible to pour good amount of the rainfall in this part of the Indian region. So this figure is basically showing the amount of the rainfall received over Indian region as per the various meteorological subdivisions defined by IMD. And if you compare these colors with the color legends mentioned here, most of the Indian region, this green color is basically the normal monsoon season rainfall, blues are the excess rainfall. So this particular part where the good amount of the rainfall was received in the beginning of the season itself because of the cyclone Biparjoy. Apart from this part of India, most of these states have received normal monsoon rainfall till 2nd of August, except some parts of Northeast India, Kerala, East UP, Bihar, Jharkhand, and West Bengal. Apart from these states or the subdivisions, most of the Indian region has witnessed either the normal monsoon or the above normal monsoon. Therefore, this cyclone Biparjoy remnant played a very important role in providing the rainfall over this region in the month of June. Here, this picture is showing another important feature of the high spatial resolution satellite data sets. This is basically the TRMM2B31 data set available from 1998 till 2018, but this has been used till 2013 here. So this data set is basically available as per the orbital passes of this particular satellite, because this is the low inclination satellite and provide data set particularly in the tropical region. So these orbital passes were combined together and interpolated at 5-kilometer resolutions. Therefore, we get this fine scale structure of the rainfall, particularly in the mountainous region of India. And if you see this rainfall structure here, this is the Uttarakhand region, this is the Himachal Pradesh region, Jammu Kashmir and Ladakh. So there is a difference in the rainfall spatial distribution in Uttarakhand and Himachal Pradesh. We see a dual band structure of the high rainfall. That is clearly visible here. So Uttarakhand rainfall is characterized as the dual band rainfall structure, whereas in Himachal Pradesh region, we note only single band rainfall structure. And if we compare this data set, this high resolution satellite data sets with the Indian Meteorological Department gridded data set, we note that this dual band structure is not captured by this data set, because this data set provided by IMD is having a coarser resolution. This is based on the ground-based measurement. And if you compare this picture with the number of rain gauges available, which has gone into the development of this product, are sparsely covered. and also the density of the rain gauges, because the color bar is showing the number of rain gauges available in every grid point. You would see there are several locations where no rain gauges available in 2019. Here we hardly have any rain gauge in the upper reaches. Here we have good amount of the rain gauges available, but again the density is not same. Number of rain gauges are not homogeneously distributed in any of the states in northwestern part of India. In Ladakh, there are hardly 3 rain gauges. Likewise, in Jammu Kashmir, we have very limited number of the rain gauges. Because of this problem, we have the coarser resolution dataset available from IMD, and this dataset is not able to resolve the structure, which is the dual band structure over the Uttarakhand region. So if we compare this rainfall structure with the elevation of this region, we also have noted that Uttarakhand, the places where the higher monsoon rainfall is reported is below 2 kilometer resolution, whereas 2 kilometer elevation basically, or 2000 meter elevation, we receive the very high amount of the rainfall. Likewise here too, we receive good amount of the rainfall, but in Himachal Pradesh, we received high amount of the rainfall in the range of 1400 to 1900 meter. So this is the variation. So this high resolution rainfall structure has nicely been captured by this satellite data set and enable us to study the fine scale spatial distribution of the rainfall and the mechanism responsible for making this spatial pattern over this region. Now the variability of the rainfall, because during the monsoon season, we don't expect the rainfall throughout the season. We also don't expect the rainfall same year to year. So these are the variability that we know during the monsoon season over Indian region. Like we know the interannual variability of rainfall. These are basically the variations of the annual cycle. Means we note that there are the few years which are the flood years, there are the years which are drought years. In between we have several normal years also. So these are the variabilities which are forced by the sea surface temperature variations, and these are basically associated with the ANSO, El Nino Southern Oscillation, or inherent variability in the Indian Ocean. So this is the variability which is also governed by the Indian Ocean dipole. There is another variability that happens in the within the season. So we call it the intra-seasonal variability, because during the 4-month season of monsoon, we experience the spells of active rainfall and the break rainfall. This is known as the intra-seasonal variability, and this active and break rainfall spells are associated with the variability which is happening at the 20 to 40 days scale. So we call them the periods of the active and break spells associated with the 20 to 40 days periodicities. Now we have diurnal variability. Diurnal variability is basically the rainfall fluctuations that happen during the day and the variations in the day and night cycle. Then we have fourth variability that we also note during the monsoon season, that is the extreme rainfall events of the cloud burst event. High amount of rainfall is poured during these kind of the events. So extreme rainfall events are the rare to rarest event that occur only 5% of the time, and this is the extreme amount of the precipitation which lasts in short span of time but is capable enough for creating the flood-like conditions. As per Indian Meteorological Department, rainfall rate equal or greater than 100 millimeter in an hour may be considered as the cloudburst event. So in the coming slides, we'll see how these variabilities can be addressed using these satellite-based data sets. To start with, we will see the interannual variability. So before we look into this, let us see this seasonal rainfall distribution at climatological scale over Indian region. So as I already mentioned that the region which is dominated by the orography is receiving the high amount of the rainfall during monsoon season. Likewise, the Western Ghats and the Northeast Indian region. Good amount of the rainfall is also received in the foothills of the Himalayas. And then we have this region. This is known as the Central Indian region. Within this region, you see that rainfall variability is not varying much. The rainfall is more or less same within this box. So this box is considered as a homogeneous box. So if we just take the mean within this box, it may be a representative of the all India rainfall. So rainfall over this region go beyond 16 millimeter per day. If we see the exact number, it is go beyond 25 millimeter per day over this region as well as over the northeast Indian region. Within this region, we get rainfall that is of the order of 7 to 8 millimeter per day during the monsoon season. So this is the climatological rainfall distribution. Then we have the rain shadow region here in the Karnataka and the Maharashtra. Tamil Nadu also does not receive good amount of the rainfall in the Indian summer monsoon, but it receives rainfall during the northeast monsoon in the winter time. This is the region in the Rajasthan, which also receives very less amount of the rainfall. So monsoon arrive here very late, and also the withdrawal phase of the monsoon also takes place from here at the beginning, around 15th of September. So here the satellite data sets have been used to find out the inter-annual variability of Indian summer monsoon using the satellite data sets. So what has been done here, the normalized index or the normalized unit have been plotted to find out that how many years during the availability of this data set were the excess monsoon years or the deficit monsoon years. So as you can see here, there are the 2 years like 2006 and 2011. These were the years where the anomalies were more than +1. So these were the excess year during this time period. And likewise, the years like 2000, 2002, 2004, and 2009. These 4 years were the deficit monsoon year, and it has been obtained using the TRMM 3B42 data set. TRMM is a satellite. The data set from this particular satellite is available for a long-term period. So that has been used to develop this normalized indices. Therefore, the satellite data sets can very well be used for the monitoring of the inter-annual variability of Indian summer monsoon. Now the intra-seasonal variability. If we just look at the past studies, we know that the Indian summer monsoon is characterized by 2 dominant periodicities, which fluctuate at a time scale of 10 to 20 days and 30 to 60 days. So here the information which is available in that time scale is being presented in the frequency scale. So these are the fluctuations here shown in the power spectrum of the rainfall data set, and you can see some dominant peak here. So below the 10 days peak, there are the more fluctuations or the high frequency fluctuations. These are the fluctuations which are associated with the synoptic scale variability that happens at 3 to 7 days time scale. But here is the variability that is happening at 10 to 20 days time scale. Likewise, there is another variability which is happening at 30 to 60 days time scale. There are other studies also which suggest that there are 2 dominant periodicities centered over 20 days and the 45 days. So on an average, we have these variabilities of the Indian summer monsoon, wherein we see the fluctuations or most of the monsoon system parameters like rainfall, OLR, winds, sea surface temperature. We find these kind of the variability in all these parameters of the monsoon system. And this 10 to 20 days periodicity have generally westward propagation. So if we just monitor the rainfall for this much time period or this particular periodicity, we find that the rain bands or the OLR bands are propagating in the westward direction. And if we see the 30 to 60 days periodicity, that moves in the northward side. And if we compare this 30 to 60 days variability of the summer monsoon rainfall with the break spell, you would find that the 30 to 60 days intra-seasonal oscillations basically represent the break spell of the summer monsoon, whereas 10 to 20 days variability is associated with the active spell of Indian summer monsoon. It has also been noted that these 2 periodicities are associated with the break and active spell, and rain and the aerosols, which are the suspended particles in the atmosphere, they also play a very important role in modifying the rainfall structure by enhancing the break kind of conditions over the Indian core monsoon zone. Now here is the application of satellite data sets for monitoring such kind of the variability which is just shown in the previous slide, that is the intraseasonal variability. Here satellite data sets from various platforms have been used, like sea surface temperature for TMI. TMI is a sensor on TRMM satellite. OLR has been taken from IIRS, and which are the monsoon system parameters, have been used here to monitor the intraseasonal variability of Indian summer monsoon. And this is the 30 to 60 days sea surface temperature intra-seasonal oscillation. So as mentioned in the previous studies based on the other data set, it shows that this 30 to 60 days variability moves in the northward direction. And when we can see that this is the orientation of the contour having the northward direction, whereas it remains stable in the east and westward side. So basically this band propagates in the northern side, that has very well been captured by the TMI data set. And if we just see that how much contribution of these variability is giving to the overall rainfall variability. So we see that the Bay of Bengal region during the drought year give more contribution from the OLR data set and the sea surface temperature data set to the overall variability of the monsoon season rainfall in this region. So 25% of the variability and also then 13% of the variability over the Bay of Bengal region come from the outgoing long wave radiation data and the sea surface temperature data. And if you see the Arabian Sea most of the time give more variability from the larger scale, this 30 to 60 days intraseasonal scale. So this is the low frequency fluctuations. So in the Arabian Sea, maximum contribution is coming from the low frequency fluctuations, whereas Bay of Bengal, we are getting more contribution from the high frequency fluctuations. Therefore, both the seas, which are surrounded by the Indian subcontinent, the Bay of Bengal and the Arabian Sea, are behaving differently at the intra-seasonal scale. Here, the active and break rainfall spells have been shown. This has been computed using the GPCP dataset. And here you can see that there are the active spells and the break spells. So there is a standard definition to define this active and break spell. These are done like this. So satellite-based dataset can be utilized to define the active and break rainfall spell. The definition was given by Rajivan et al. In 2010. And as per the definition, if the area average daily rainfall anomaly, which is standardized by its own daily standard deviation, is less than -1 or +1 for successively or consecutively 3 days or more, that spell may be considered as break if it is below -1, or active it is higher than +1 of the monsoon season. So here the gray bars are basically the active and break rainfall spells if the fluctuations are given beyond the +1 and the -1. So here we have the active spells which are very well fitted by the 10 to 20 days oscillation. So already I mentioned that 10 to 20 days periodicity of Indian summer monsoon is associated with the active spell. And the periodicity that happens at the 30 to 60 days time scale is actually responsible for governing the break spell of the Indian summer monsoon. So in this picture, the composite of the active and the break rainfall spell has been shown. As per the standard theory, so during the active spell, the central Indian region or the core monsoon zone receive very good amount of the rainfall. At the same time, we witness less amount of the rainfall in the Western Ghats region. But during the break spell, this is the Western Ghats region and the foothills of the Himalayas that receive good amount of the rainfall, but central Indian region remains rain deficit. Now there is another method to see the variability of Indian summer monsoon in terms of the various dates corresponding to the 10%, 50% and the 90% of the seasonal total rainfall. These are basically dates. Generally, when people study the variability of the monsoon season rainfall, they just study the intensity of the rainfall or amount of the rainfall. These are basically the dates. So that can also be defined using this method. And if we see the northwestern Himalayan region, we see that the seasonal mean is also witnessing some changes over this region in the recent 20 years as compared to the first 20 years. And overall, if we see that the changes are also being observed in the arrival of these dates, like 10% of the monsoon season rainfall over this region of India, the northwestern Himalayan region, on average, the date is around July 5, which is very close to the onset date. So about 10% of the rainfall is received till the first week of July itself. About 50% of the seasonal total rainfall over northwestern Himalayan region is received by July 31st. So the July season remained very, very active, likewise the August as well. But in the September season, we received less amount of the rainfall over this region, and 90% of the monsoon season rainfall received by September 12th. So if we just see how these dates are varying over the last 40 years of the time period, we can see that there is an early arrival of the 10% of the rainfall and the 50% of the rainfall in the Uttarakhand and Himachal Pradesh region. So we find that the monsoon arrival actually appear to arrive early over these locations in the Indian subcontinent. So climatologically, if we see, because we have used here the 40 years of the data set. So in the 40 years of the data set in recent year, there are some significant changes are being observed in the arrival dates over this part of the Indian subcontinent. Now the diurnal variability. So this is the important feature of the satellite data set, that it actually helps us to analyze the variability within a day. So here the data set which has been used is the TRMM3B42 version 7 data, specifically over the northwestern Himalayan region. So what we see here that the usually heavy rainfall events occur from late night, 2:30 Indian Standard Time, or in the early morning hours. This is the 5:30 in the Indian Standard Time. So 5:30 and the 2:30 are the time period where we receive high amount of the rainfall in the northwestern Himalayan region. And we also see other peaks as well, that is during the afternoon around 2:30 as well as 5:30 in the evening. But if we compare this 2:30, 5:30 with the early morning 5:30 and the late night peaks, the amount of the rainfall is less here. So we call these peaks the secondary peaks, the 2:30 p.m. and the 5:30 p.m. Whereas the early morning peaks, this 5:30 and the 2:30 peaks, are the intense enough. So this afternoon peak that happens in the 2:30 time or the 17:30 time, that is basically the orographic rainfall, because during the afternoon what happens, the mountain surface becomes warm enough and gives rise to the atmospheric instability that results in the deep convective cores by promoting the free convection and generate the cumuliform clouds that pour rain through this orographic rainfall processes. Whereas this early morning peak, this 5:30 a.m. and 2:30 a.m., these are the peaks which are also known as, particularly the 2:31 as a nocturnal peak. And this is believed to be due to the convergence of katabatic winds. Katabatic winds are nothing but the downslope winds, because there is an interaction of the downslope winds and the warm moist monsoon winds coming from the southeast during monsoon season, and the interaction of the winds with the warm moist current coming from the Bay of Bengal during the monsoon season is responsible to give high amount of the rainfall during this time period in the Uttarakhand region of northwestern Himalayan region. Likewise, we also observe one peak in Himachal Pradesh as well. So here also, reason being the same, in the night time, we have the katabatic winds here, and there is an interaction with the warm moist current coming from the surrounding seas. And if we see the rainfall peaks and compare them with the altitude, we find that the rainfall peaks in the Himachal Pradesh region, here and also here, these are restricted up to 3000 meter, means beyond 3000 meter height in the Himachal Pradesh, we don't observe the high peaks of the rainfall. But over Uttarakhand region, we see that in several occasions, the rainfall peaks are also being observed over the elevation, which is more than 3000 meter altitude. So that's how the distribution of the rainfall over these two mountainous states of India are different at diurnal scale. Now, there is the fourth kind of the variability, that is the extreme rainfall events or the cloudburst event, that can also be very well analyzed using the satellite data set. Even in some of the cases, we find that the satellite data sets are more suitable because we are finding the information at a very fine scale resolution. So how to define an extreme rainfall event? Extreme rainfall event are nothing but the rare events, and there is no standard definition. If we see this distribution of the meteorological data set, this could be rainfall or the temperature. This is just only for the illustration purpose. It may not be the exact distribution of any meteorological variable. This is being shown only for the illustration purpose. So you can see a large tail here. So extreme rainfall events are defined as the events which are rare to rarest and which lie towards the tail of the distribution. So these are the events which are the extreme events, and we can categorize them further using different standard definitions. However, earlier people have used the objective definition to define the extremes, like they have taken a specific threshold like 150 millimeter per day or 100 or 150. But now people are also using the statistical based or the high quantiles like 99th percentile, 99.5th percentile. This can be utilized. Apart from that, World Meteorological Organization has given different other indices to find out the extremes like maximum 1 day precipitation, maximum 5 day precipitation, or precipitation due to very wet days or very, very wet days. Likewise, Indian Meteorological Department has also given or categorized the rainfall in 3 different categories: very heavy rainfall ranging 124 to 244, extremely heavy rainfall that is greater than 244 millimeter per day. Then we have cloudburst event or the extreme rainfall events. These are the events where we note the rainfall greater than 100 millimeter in 1 hour. So the application of the satellite data sets are shown here for the Western Ghats region. Here what we note here is this: the seasonal mean rainfall is maximum over the Karnataka region, the coastal Karnataka region. If we compare 3 Western Ghats states, the Kerala, Karnataka and Maharashtra. So among at seasonal scale. And if we see the high percentile of these events, like 99.5 is about 120 millimeter per day approximately, and 99.75 is about 150 millimeter per day. And if we compare the spatial distribution of the number of events over the Western Ghats region, we find that heavy rainfall events are more in the coastal Karnataka, but extreme rainfall events, which are more than 150 millimeter per day, these are the number of events shown here in this color bar. We see that the number of extreme rainfall events, which are in the category of 150 millimeter per day or more, are more in the Maharashtra region, whereas the seasonal mean rainfall was more in the Karnataka. Therefore, we don't find any relationship between the mean monsoon rainfall and the number of extreme rainfall events happening over a particular region. Likewise, we also have seen the extreme rainfall events over the Uttarakhand region. You also have seen the climatological distribution of the rainfall, that rainfall highly spatial variable quantity over Indian region. Likewise, if we compute the thresholds of the extremes over Indian region, we find that there is a high spatial variability as well. So here, if we compute these thresholds corresponding to high quantiles, we note that Uttarakhand region is giving high amount of the rainfall corresponding to the 3 percentiles, whereas Himachal Pradesh is giving lesser value. Jammu Kashmir is much lesser than that, and if we just take northwestern Himalayan region as a whole, we find lesser amount of the rainfall, which is lying at the 90th percentile, 99 or 99.99 percentile. Using these values, if we see the rainfall distribution or the number of events distribution in this region, we note that the high frequency of the extreme rainfall events are generally happening the region below than the 3000 meter elevation. So here we have the elevation lesser than 3000 meter. And if we compare the states here, the northwestern Himalayan region states, we note that Uttarakhand is the region which experience higher number of the extreme rainfall events than the Himachal Pradesh, and then come the Jammu Kashmir, and towards the end we have the Ladakh region. And there are few locations like Kangala, Hamirpur, Sirmaur, Nainital, Udham Singh Nagar and Champawat. These are the districts which are highly prone to the extreme rainfall events. So this kind of the analysis, which is done at a very high spatial resolution, help us to find out the locations which are prone for the extremes. This kind of the analysis is also useful for the policymakers to plan the infrastructure and other development in this region. Now here the another potential of the satellite data set have been depicted. So here the OLR data set as well as the brightness temperature from the satellite has been shown. So a cloudburst event was reported in the Mori Tehsil in Uttarakhand region, and for this event this analysis has been done. This shows that the OLR drop of the order of 120 to 80 watt per meter square in a short span of time is associated with the high amount of the rainfall. So such kind of analysis help us to find out the direction of the propagation, dropping the OLR. Kind of the analysis can help us to find out the precursors of the rainfall happening over the potential locations, specifically in the Uttarakhand and the Himachal Pradesh during the monsoon season. So this analysis has further been extended using the cloud top temperature and cloud top height. So we have noted that the drop in the outgoing long wave radiation is actually in association with the increase in cloud top height that can go up to as high as 20 kilometers, and there is a decrease in cloud top temperature in association with the enhanced rainfall. And if we compare the ISCCP cloud classification scheme, we find that most of the events which are the cloudburst event are the deep convective or middle level nimbostratus cloud. So based on the high quantiles, we note that outgoing long wave radiation of the order of 100 watt per meter square is associated with 250 millimeter per hour rainfall in this region, particularly the mountainous region of Himalayas, the Uttarakhand and the Himachal Pradesh, where the cloud top temperature can go as low as 207 Kelvin and cloud top height can go as high as 19.6 kilometer or approximately 20 kilometer. Here we see the number of events that were reported in 2022. So Uttarakhand is the region which received maximum number of the cloudburst event during the monsoon season. Then comes the Himachal Pradesh and Jammu Kashmir, and Ladakh is basically a cold desert that also has received some 5 cloudburst event in the year 2022. Okay, the potential of the satellite dataset is depicted for the Leh cloudburst event, and it is noted here is the propagation of the rain bands in this region were nicely captured by the inset-based dataset. Intra-seasonal variability of the Indian summer monsoon is found to be associated with the aerosol. So aerosol are actually the regional contributor. So these are basically the active spell. So the composite of the active spell for the year 2007 has been taken up, and then the rainfall distribution has been compared with the cloud optical depth, cloud effective radii, cloud fraction, aerosol optical depth, and single scattering albedo. So we have noted from this analysis that this is possible that the variation in the cloud properties that we note during the active and break rainfall spell is basically because of the availability of the aerosol that is modifying the cloud microphysical properties and then deciding the amount of the rainfall during the active spell or the break spell. And if we see the break trajectory analysis for such events, we have noted that these are the continental or the marine aerosol that or we find the rainfall, it is noted that the aerosol actually plays very important role in modifying the distribution of the high amount of the rainfall, its depth and duration. Likewise, it has also been noted during the break spells that the cloud fraction, even though it was higher over the central Indian region, but amount of the rainfall very less, and it came under the category of a break spell. And for this particular event, we have noted that the most of the aerosol during this time were the continental aerosols that actually lead for the formation of this break spell for the year 2009. Now, for this, the role of the natural dust aerosol have also been explored using the satellite-based dataset. So here the correlation between the central Indian rainfall found to be highly positive with the aerosol loading in the Arabian Sea and the Arabian Peninsula. So here main source of the aerosol is the natural dust aerosols. So these natural dust aerosols actually having a very high correlation with the central Indian rainfall. So central Indian rainfall is not only being governed by the aerosols available over this region, but it is having some remote connection with the distant aerosols. So here the data set has been used that is coming from the MODIS and the MISR sensors of satellites, and the significant correlation have been noted for these two parameters. Rainfall is taken from the GPCP and aerosol is coming from the MODIS and MISR. So the satellite data set actually served as a basis for the researcher to get more insight into the physics of the monsoon rain and distant aerosol relationship. And the satellite data set also enable us to diagnose the important covariability between these two parameters, and it helps us to understand the variability in better sense. So given that the covariability that we observed using the satellite data set, here the model experiment have been conducted Northern Africa and West Asian region. The Indian summer monsoon rainfall also witnessed a decline in the rainfall during monsoon season. So this relationship is happening at a 7 days time scale. If you suppress the dust here, after 7 days of this suppression, decrease in the rainfall over Central Indian region is noted. And this finding is also supported by the satellite-based observations. Now the cloud liquid water, this is the hydrometeors. This is available from the satellite TRMM microwave imager. And this particular analysis shows us that over the Arabian Sea, which is a orographically influenced ocean, and if we compare the amount of the rainfall with the cloud liquid water, this is the cloud liquid water, this is the rainfall. See, we find that the higher cloud liquid water for a lower range is found over the Arabian Sea, whereas the high amount of the rainfall in the Bay of Bengal is associated with the high amount of the cloud liquid water. So cloud liquid water plays a very important role in the precipitation formation, as well as the cloud liquid water has been analyzed using this TMI dataset for the active break to active and active to break phases over Central Indian region. And it has been noted that the cloud liquid water is very high during the active spell. It also found to be high when there is a transition from break to active spell. So this is black line is for the break to active spell. So amount of this cloud liquid water for this time period was responsible for the formation of the cloud droplets that subsequently give good amount of the rainfall once that transition is completed from break to active. Here authors also have noted for this enhanced cloud liquid water during this phase break to active, the aerosol also play a very important role, because aerosols provide a surface to the moisture available in the atmosphere, and they act as the cloud condensation nuclei. The moisture available in the atmosphere deposit over these particles and then form the cloud droplets that subsequently help in the precipitation formation processes in the Central Indian region during the change phase from break to active. Now, satellite data sets also provide very rich information over the oceanic region in the form of the sea surface temperature data set and also the sea level data or the sea surface height. Here in this animation, the movement of the warmer water from the western side to the eastern side is shown for the year 2023. So in this year, there is a development of the El Nino in the Pacific region. Normally, the Western Pacific region is the region of warm water, but during the development phase of the El Nino, there is a movement of the warm water from the western side to the eastern side through the Kelvin wave, and that has naturally been captured by this particular satellite Sentinel-6. And this animation shows a series of the waves called the Kelvin waves that move the warm water from the western side to the eastern side. So this is the evolving phase of the El Nino. Now El Nino is there in the Pacific region in 2023, and it is anticipated that it may impact the Indian summer monsoon rainfall in coming days. Likewise, El Nino La Nina, we also have another important impact formation in the Indian Ocean, that is the Indian Ocean dipole. So this particular event actually modify the impact of El Nino and the La Nina over Indian summer monsoon. So Indian Ocean dipole, if it is forming along with the El Nino, it would try to suppress the impact of El Nino, because Indian Ocean dipole positive phase also enhance the rainfall over Indian region in the Africa region, and if it is in the negative phase, we don't expect good amount of the rainfall over Indian region, whereas we expect the low amount of the rainfall over Indian region. So these two variabilities can be very well captured by the satellite data sets, and the sea surface temperature and the sea level height data set help us to monitor such kind of the variabilities, specifically for monitoring the evolving phase of these variabilities in the Indian Ocean and the Pacific region. So with this, I thank all the participants for attending this lecture. Now we'll take